Hi, this is an AP chemistry video. This is going to be part 4, I think, of topic 4.5, stoichiometry. So here is a problem where we're going to be looking at a formation of a precipitate and concentration of ions. So it's a little different than what we've done so far. But it's still really the same process, figuring out who the limiting reactant is, determining, this time we're going to determine how much is excess and calculate the molarity. So first thing you have to do always, if not given, is write the chemical formula, balanced chemical equation. So we have sodium sulfate, which is aqueous, going to react with lead 2 nitrate, also aqueous, double replacement. We're going to get sodium nitrate, aqueous, and then we're going to get lead sulfate. That is going to be our precipitate. I would also balance by putting a 2, and I think that's it. So first thing I'm going to do is use these beginning amounts and calculate moles. So 2 liters times 0.0250 molarity, so moles of sodium sulfate per liter. So that gives me 0.0500 moles of sodium sulfate. And then 1.25 liters of the lead 2 nitrate, which is 0.0500. So there's that many moles of lead 2 nitrate in a liter. So that gives me 0.0625 moles of lead 2 nitrate. Now I'm ready to determine the limiting reactant. So I am going to take my moles of sodium sulfate and convert to my moles of lead 2 nitrate. And I know it's an easy 1-to-1, but I would still need to show that or talk about it in the question. So I get 0.0500 moles of lead 2 nitrate would be needed to react with all of that sodium sulfate. And when I look up here, you can see that I do have that. So that means the lead 2 nitrate is my excess and the sodium sulfate is my limiting. But let's go the other way in case you chose to go that way. Let's take our moles of lead 2 nitrate. And I know it's a 1-to-1. It's kind of silly, but we will show our work. So I would need 0.0625 moles of sodium sulfate to react with all of that lead nitrate. And you can see that I don't have that. So that means this is my limiting. I'm not going to use that number at all. And then the lead 2 nitrate is my excess. So in the question, they want to know what is the concentration of the lead ions. Let's figure out how many moles of our excess reactant we have. So we started with 0.0625 moles of lead 2 nitrate. And so that's how much has been given. And then up above, we know that we're going to use 0.0500. That's how much will actually be reacting or used up. So that means I'm going to have 0.0125 moles of lead 2 nitrate left over. So we know, if we want to know the molarity of the lead ion, we know that if I have this 0.0125 moles of lead 2 nitrate, then I have 1 mole of lead ions for every 1 mole of lead 2 nitrate. So that gives me 0.0125 moles of lead ions. And we want molarity. So we will take those moles and then divide by the total volume, which in the beginning part of the question, if you remember, we have 2 liters and 1.25 liters. So when I divide that, I get 0.00385 molarity. Sometimes it's helpful, like, to draw a picture, you know, how, so we made lead sulfate is the precip, and then we've got our spectators, you know, the sodium and the nitrate ions, but we also have the extra lead ions. So that was what, can't write, that's what we were calculating, was how much of the molarity of them were left over. Let's do a similar problem. Let's see if I'm ready for this one. I am not. Let me add a page here. So this is a nice long problem. Again, so here we go. And this one kind of breaks it up and tells you what to do. I'll kind of follow the steps, and then when we can't see them anymore, I'll copy them and bring them down. So let me get that bigger for you. Okay, so I would want to write the balanced chemical equation. So we've got aqueous potassium hydroxide mixed with aqueous magnesium nitrate. And we are going to get potassium nitrate, which we know is aqueous. And we're going to get magnesium hydroxide as a precipitate. So then I would want to balance. So that is my balanced equation. What is the precipitate? The precipitate is the magnesium hydroxide. Number 3, now we're going to determine the limiting reactant. So I'm going to take my 100 mils, convert it to liter, and use my molarity to figure out how many moles of potassium hydroxide I have. And then I'm also going to do the same for my magnesium nitrate. And when I do that, I also get the same answer. Oops. So now that I have them in moles, I'm going to determine my limiting. So I am going to take my moles of potassium hydroxide and I am going to convert that into moles of magnesium nitrate. And when I do that, I get 0.0100 moles of magnesium nitrate. And you can see that I have plenty. So I know then that the magnesium nitrate is my excess reactant and the potassium hydroxide is my limiting. Let's say you went the other way. So you started with your magnesium nitrate and you calculated how many moles of potassium hydroxide would be needed to react with all of it. Then you're going to get 0.04 moles of potassium hydroxide. And remember, we only have 0.02. We're not going to have that and use that number. Our limiting reactant is the potassium hydroxide. Excess is the magnesium nitrate. Next, they want us to write the net ionic equation and draw a picture. So the net ionic is going to be just the magnesium ions plus the hydroxide ions forming magnesium hydroxide, solid precipitate. If I were to draw this in a beaker, you can see that our precip is the magnesium hydroxide. And we're going to have our spectators. So we will have the potassiums left over. No leftover hydroxides because that is our limiting reactant. The potassium is there because it's not really a reactant, it's a spectator. We're also going to have nitrate ions. And we are going to have some excess magnesium ions. So that is why we're going to be able to then calculate how much of that magnesium ultimately that we had left over. So all of the hydroxide from the potassium hydroxide, the limiting reactant, went into the precip, but we had excess magnesium nitrate. So there's excess magnesium ions that were not able to form magnesium hydroxide because the potassium hydroxide ran out. So let's pull the question down now. So let's figure out how much magnesium ion we started with. So we know, and again, this is a little repetitive, but we have the 0.2 molar magnesium nitrate. And then we have 1 mole of magnesium ions for every 1 mole of magnesium nitrate. So, my beaker's coming with. Let me get rid of my beaker and redraw it over here. Okay, so that gives me 0.0200 moles of magnesium that we started with. How much reacts? Remember, let's grab this so we know we're working on how much of the magnesium actually reacted. We would start with our LR. So we know that we have 0.0200 moles of potassium hydroxide. So I'm going to do my mole ratio. Oops, 2 moles of KOH. And then similar to the previous, there's 1 mole of magnesium ions for every 1 mole magnesium nitrate. So when I do that, I get 0.0100 moles of magnesium ions. So calculate the leftovers. Let's do that. So all we're going to do there is take our 0.0200 moles of magnesium that we had to start with, subtract the amount that's going to react, and then we get 0.100 moles of leftover excess magnesium ions. So the last part of the question is we're going to calculate the molarity of every ion that remains in the solution. So let me grab this so we remember what we're doing. So we can remember our drawing up above. We can calculate the molarity of the magnesium ion by using the leftover moles and dividing by the total volume, which was 200 milliliters or 0.2 liters. So my molarity of my magnesium is 0.0500 molar. Remember, I also have the nitrate ions and the potassium ions. So if I want to determine how many moles of them I have, I would start with my LR. And I know that I have 1 mole of potassium for every, not my LR, just start with the potassium hydroxide, and then the ratio of potassium ions to potassium hydroxide is 1:1. So that means I'm going to have 0.02 moles of those spectator potassium ions. So I can easily calculate the molarity of the potassium by taking 0.02 mole per 0.2 liter. And that would give me 0.1 molar of potassium ions, molarity of potassium ions. To figure out the moles of the nitrate, let me switch to another color. So we know that we had 0.0200 moles of magnesium nitrate. So this time we're going to realize that we have 2 moles of nitrates for every 1 mole of magnesium nitrate. And so then that gives me 0.04 moles of nitrate. So to calculate the molarity of the nitrate, it's going to be 0.04 moles of nitrate ion per total volume. It's 0.2 liters. So I end up with 0.2 moles per liter of nitrate.